This is probably my favorite part of all of Chem 229, this part because your brain really has to get used today. So hopefully your thinking caps are on and you're ready to think today. Okay, so we ended last week with the cell notation. So let's just review cell notation really quickly. And again, we use it for our voltaic cells. The electrode, that's going to be our solid. And remember, our oxidation's always going to be written on this side, and our reduction's always on this side. So this is the electrolyte. This is the one that's the aqueous, and this is the one that's the solid. And again, oxidation's always going to be on the left, reduction's always on the right. This just means the difference between the electrode and what's ever in. So like if you have your beaker, and you have an electrode, this line right here just means they're in the same beaker, but a different phase, solid versus aqueous. This is that salt bridge that connects the two. And if you have multiples in the same phase, we're going to use commas, and I'm going to show you how that works in just a minute. Okay, so now, and we'll talk about what this inert electrode is in just a minute. Okay, so here's our voltaic cell. Again, so in here we have our zinc 2+. And again, I'm just ignoring my nitrate because it doesn't matter, right? Net ionics, just net ionics here. And then we have our zinc solid. So here's our zinc, here's our oxidation. There's our solid electrode. Here's what's in the beaker, zinc 2+ AQ. This is like the divider between the two, the salt bridge. So this is the salt bridge. And we don't even need to write, you don't need to know what's in the salt bridge. It's some soluble ionic compound. That's all that matters. You can literally choose any soluble ionic compound you want, as long as it's not part of the reaction. NaCl, KNO3, KCl, like you could choose anything. All right, salt bridge, that again joins the two. Here's what's in the aqueous solution. So right again, here's about the nitrate, don't care, this is Cu2+. That's what's in there. And then again, here's the barrier between the aqueous and the solid. That's this. And there's our other electrode. And this is our reduction. Okay. And again, remember cathode, reduction, Leo, the red cat. Reduction happens at the cathode. Okay. Now, let's talk about these electrodes. So remember our anode, where there's oxidation, is made of the metal that's oxidized, and the cathode, right, is made of the metal at the reduction. But sometimes we have an ion that's in an aqueous solution, and it is being oxidized or reduced in the aqueous state. So it's going from one oxidation number to another oxidation number, but both of them are in the aqueous state. And I'm going to show you an example of that. But we have to have a place where the electrons can be transferred. So we need some kind of a solid surface where the electrons, where the reaction can take place. So nothing's actually happening at the surface, like to the metal itself. All it is a conduit where the electrons can kind of like stop over and, oops, they can stop over and drop off their electrons. Okay, so again, it doesn't participate, it's just lending a surface. So most common reaction for this is, or the most common electrode, platinum is what you're often going to see because it's very inert. And so in this case, you can see that you have manganese right here, that's a +7. Again, this is what your quiz will be on this week, like what's the oxidation state. It's going from a +7 to a +2. But if you look here, this is aqueous and this is aqueous. So we need a place for this reduction to take place. And so what happens is both of these are in the solution, but the transfer takes place on the platinum electrode. Now, again, the platinum electrode isn't actually involved in our reaction. It's just a place where the, sorry, my computer's going crazy. It's just a place where the electrons can be transferred. Okay, so if we look at this, our oxidation here, again, this is our aqueous here. Here's our electrode, so here's our oxidation. No, sorry, my computer, it hates me. Hold on, let me try and fix this. Zoom updated. Let me tell you, my computer does not appreciate it. Okay, so, all right, so now, try to fix this side. So now when we see this here, this is our oxidation. Oxidation, my pen, Zoom, my computer, not friends. Here's our reduction. This is our solid electrode. That's our iron. Here's what's in the solution. That's our salt bridge, right? There's our salt bridge. And then in this solution, you can see we have MnO4 aqueous, we have hydrogen aqueous, and we have Mn2 aqueous. We separate them, they're all in the same phase using commas, right? So all of these aqueous, again, are separated using commas. And then our inert electrode, we still write. So there's our phase change, and this inert electrode is a solid. And so we still write this one. And again, most often our inert electrode is platinum because it just works really well. So again, when we're doing this, remember oxidation on this side, left, reduction, right, solid, aqueous, salt bridge, aqueous, comma, aqueous, comma, aqueous, line, solid. Pretty much how cell notation goes. Now, we're gonna look at cell potential here for a second. And this is when everything starts getting more fun. Sorry, my computer's literally going crazy. You could only see what it's doing. It's like a crazy computer right now. Okay. Now, what we're going to try and do is we're going to try and figure out, so if we have a half reaction that has a strong tendency to occur in the forward direction, it will have a positive potential. But what about if we have two half reactions like here, right? So we have two half reactions in this case. How do we know that the electrons will go this way? How do we know it will happen? How do we know this will occur? So yes, I've written it and I said this is oxidation, this is the reduction, but how do we know it's occurred? So that's what we're going to try and figure out. Will it happen or won't it happen? And so we're going to look and see if it's spontaneous or non-spontaneous. And remember, if it's spontaneous in one direction, it's non-spontaneous in the other, vice versa. So when you see this here, so copper, actually, we're going to go this one. So this one, you're going to see, and this is what we're going to try and answer right now. So this is non-spontaneous in this direction, but it will be spontaneous in the other direction. So this is what we're actually going to look at. Okay, so our copper has a more positive potential than the She. And I'm going to talk about what the She is in just a second. So our copper has a positive potential, which means that the anode, where oxidation takes place, has a lower potential energy than the cathode. And so the electrons will not spontaneously flow from the anode to the cathode. So just like in any kind of I don't know, think of like a waterfall, right? The waterfall, it's always going to go from higher potential energy to lower. The water's always going down the waterfall, right? Higher, lower potential energy. Same thing with the electrons. It's always going to go from higher to lower, right? It's always going to go from higher to lower. So if this has a lower potential energy, it's not going to go backwards. Water's not going up the waterfall. Not going to happen, right? And that's what this non-spontaneous is. And we're going to spend this whole day trying to explain like that concept I just said, because the first time you hear it, you're like, how do I know potential energy? I don't understand. We're going to go through all this. So basically, and I'm going to say this a few times today, the more negative the electrode potential is, this is a potential, right? The thing with the volts, the more negative it is, that means that the greater the potential energy of the electron. And if it's more negative, we have to remember that negative repels negative, right? So electrons are more likely to be repelled by it, meaning if they're being repelled by it, it's more likely to be oxidized. Now, the more positive the electrode is, meaning cathode, anode, electrode, the lower the potential energy is. and the lower potential energy of an electron at that electrode. Because remember, positive attracts electrons. So it's more likely to be reduced because gain electrons reduce. So we're gonna develop this. So in this case here, you can see that we have, under standard conditions, zinc has a stronger tendency to oxidize than copper. And why? Because it's more positive. And we're going to look at this. And we're going to talk about why. So therefore, the electrons will flow from zinc, making zinc the anode. Okay, so the question is, what we're going to try and figure out right now is, how do we tell this? Right? So this is true, and we're going to come back to this. The question is, how do we know? So that's what we're going to work on today. First, I told you I would tell you more about this thing called the SHE. It's called the Standard Hydrogen Electrode. And I'm sure I've got that written somewhere here. Okay, so we developed this electrode. Well, not we, chemists, way before me, physicists. There it is. Standard Hydrogen Electrode. We call it the SHE. So it's 1 molar hydrochloric acid, hydrogen gas, and platinum. So when we have an electrode, we can't measure it. We can't measure it, but what we can measure is we measure the difference between the two, right? So what we can measure is we can measure the difference between this and this, but we can't measure it individually. And so what we did with the SHE is we arbitrarily assigned the potential difference of the SHE as 0. And then what we did is we hooked up all of the reactions. We made our voltaic cell with a SHE on one side and then got the reduction potentials. So let me show you what that means. So here's our SHE right here. You can always tell your SHE because it's got hydrogen and it's got platinum right here. Like this is platinum. And I mean, it's the only thing that hydrogen is being bubbled through, right? It's just, it's an odd electrode, right? So this is our SHE. And so we said this is 0. And so that means that any potential difference, that's our potential, any potential difference is the result of this reaction because we're defining this one as a 0. So that means that our reduction potential of our zinc is 0.76, right? And so then what they did is, I'm going to show you this in just a second. I just want to show you this picture really quick. So what they did, I'm coming right back to this. What they did, here are all of these reduction potentials. They measured against the SHE. So they just did what I showed you with all of these reactions, and that's where they're going to get all these numbers, right? So they did. So they had the SHE on one side, and they had all those other reactions on the other side. And then they measured these numbers and then made a nice table for us, which was very handy, and we're going to be using it all day. Okay, so now let's summarize what we've talked about so far. And then we're going to go back and explain it again after we understand this table. Okay, so the SHE, we just decided arbitrarily to call it 0. 0 volts, that's the electron potential, 0. And then we compared the SHE, we hooked it up, right, with a voltaic cell with all of the other electrodes under standard conditions. So if the half reaction had a stronger tendency to reduction, then it ended up with a positive value. If it had a stronger tendency to oxidation, it has a negative value. Okay, so first of all, we had to decide a way to write all these reactions, which was universal to everyone. So they decided to write all the reactions as reductions. So oxidize or reduce, the table is all in reductions. So we're going to talk about this. So if it's an oxidation, all you do is you flip the reduction. So let's look at that. We're going to look at this and then we're going to come back to this again. Okay, so here is the table. So for example, you're going to see here, these are all written as reductions, right? Reduction gains electrons. Look, gain, right? Look at these. Electrons. And here's the second half of the table. Electrons, right? Everything is written as a reduction. Doesn't mean it's going to go that way. We just needed a universal way to write it so everyone knew what we were talking about. Otherwise, the numbers, the positive, negative, they become very confusing. So now let's look at our first one. Just let me erase all this. So if you look at this, the higher, so here's our electron potential. That's our potential. It's a volt, right? Here's our potential. This is our half reaction. These are stronger oxidizing agents up here, or weaker reducing agents, however you want to say it. So I like to say it with reduction, right? Reduction, gain electrons reduction. So the higher they are, or the more positive they are, do you see how this is 2.8 down to 0.4? The more positive it is, the more likely it is to be reduced. Now, why the more positive it is, the more likely it is reduced? Because remember, reduction means gaining electrons. Gaining electrons, this is positive. Electrons are attracted, right? Opposites attract. So the more positive it is, the more the electrons are attracted to it. If the electrons are attracted to it, right, that means it's gaining electrons. The more positive it is, the lower the potential energy. So the more positive it is, the lower the potential energy. Now, again, the higher. So I say this two ways. I either say the higher on the table or the more positive it is. So I'm going to keep using both of those because I'm not sure which one gets through better to your brains. So the higher it is, or the more positive it is, the more likely it is to go in the forward direction, right? So up here, this reaction has an electron potential of 2.87. So it's very positive versus, I don't know, let's use this one because we all got to have this one in our lab today or last week or Wednesday. This one isn't as positive. Right. So if we paired these, if this was a reaction, so if this was an electrode, these two, put them in their beakers, have the solids, right? Put them in there together. One of them has to get oxidized, the other one has to get reduced. Well, this one is more positive. It has a lower potential energy, right? This one is less positive or more negative, lower on the table, right? All of those things are true. It just kind of depends on which way your brain likes it. So it's lower on the table, it's not as positive, or you could say it's more negative. So this one's actually going to have a higher potential energy. And electrons always like to go from high potential energy to low potential energy, right? And so therefore, oops, I want to keep these together. This one, again, the higher it is, the more likely it is to go in the forward direction. So this one is more likely to be reduced. Well, the lower it is, the more likely it is to go in the reverse direction. So this one will actually flip. This one will actually flip. And then it'll end up being, when we flip the reaction, we flip the sign. And we're going to talk more about this. And again, the higher it is, the more positive it is, the lower the potential energy, all these ways to say this, the greater the ability, or the increase the ability of being reduced. Okay, so let's look at the other half of this, and I'm going to keep saying these words and hopefully they'll sink in. Oh, I'll talk about the metal one in just a second. Okay, so now this is the same table. I just couldn't get it all on one page. So this is think of this as the top half of the table, and now I'm going to show you the bottom half of the table. So I think like some of them are actually on there twice. No, I cut it off. Perfect, didn't I? I did cut it off. Okay, this is the second half of the table. So you can see here's our She. Oops. There's our standard hydrogen electrode right there. There it is. Now, the lower it is on the table, the more negative it is, or the less positive, however you want to say it, the higher the potential energy. So you can see these are negative, these are high potential energy. The negative charge repels the electrons, right? So the electrons don't want to come towards this electrode. They would like to go away from this electrode, right? This is lose electrons, oxidize, right? This is why the electrons go away from the oxidation. They lose, the reactions lose electrons because they are negative electrodes, and electrons don't want to go towards negative. They want to go towards positive. So the more likely, so the further down we are on this table, the more likely the reaction is going to go in the reverse direction. Because remember, these are all written as reductions, right? Everything here is written as a reduction. So the reason this goes in the reverse direction is because these are more likely to be oxidation reactions, right? So they're more likely to go backwards than they are the way they're written. And again, we wrote them this way, well, not we, chemists and physicists wrote them this way because they needed a universal way to write the reactions. So they just decided we're going to write them all as reductions. They could have written them all as oxidations, but they didn't. They said all as reductions. But just because they're written in this order, right, it doesn't mean that they go in this order. And so it means if they occur in the reverse, so like, for example, this one occurs in the reverse, then we flip that sign also. Okay, now again, the lower on the table, or the more negative it is, or the less positive it is, right? All three of those are the same thing. The increased ability to be oxidized. So the more likely it is to be oxidized, the more likely it is to lose electrons. Remember, the more negative it is here, the higher the potential energy, and the negative charge repels the electrons. I know I tried to write this in here. Okay, that's a lot in our brains. So we're going to keep talking about this. Let's talk about acids real fast. So the She is at 0. Any metal below this will dissolve in acid. Any metal below here will dissolve in acid. So we can get all of these to oxidize in an acid. Remember, oxidize, lose electrons. So these are all gonna flip in an acid, right? Because this is like hydrochloric acid right here. So if this one goes forwards, then all of these paired with it will go backwards, meaning they'll all be oxidized, meaning they're going this way, they're going to dissolve from the solid to the aqueous states. But nitric acid is a special acid. I'm going to go back up here. Nitric acid is right here. This is the line for nitric acid. Nitric acid can dissolve all of these too, right? So nitric acid can dissolve everything, but it can actually not dissolve everything, but it can obviously nitric acid can dissolve everything on this table, except for obviously hydrogen, but any metal. That's why, you think about this, in our lab, we have the concentrated hydrochloric and then the concentrated nitric. And I always say, I'm like, oh, and when you come to me, you're like, I can't get this clean. And I'm like, okay, well, try putting some hydrochloric in it. And I'm like, and if it doesn't get clean, put some nitric in it. Because look at what nitric can dissolve. It can dissolve copper. It can dissolve your manganese. This brown is impossible to get out. It can dissolve iron, silver, right? It can dissolve so much more than your hydrochloric. Now, again, if can't do those though, right? So I always say if you can't get it clean with nitric, you're not getting it clean, right? And so that's why we actually have those in the lab for you. Hydrochloric, because a lot of stuff can be oxidized by hydrochloric, but nitric, because it's excellent to being oxidized. Okay, so we can come back to this if you have more questions, and you may have more questions on this because it's a lot in your brain. I hope you're writing some of this down because it's going to take you a while to look at it before it sinks in. Okay, so now how do we calculate the cell potentials. So when we have a voltaic cell, I just have numbers there for you. And I was like, right, like I just said 0.76. How do we know that, right? In that case, that one was against the sheet, and you could just look at the table and know it's 0.76. But what about when we pair two of our equations together? So some books do this a little bit differently than I do, but I just say you add the oxidation plus the reduction. Easy as that. And I'm going to expand on this more. Very important here. When you're adding these E values, you never, ever multiply when you get them to balance. So for example, when we were balancing our oxidation reduction reactions, right, we would, multiply by a number and then, right, to get them to cross off. And Hess's law, remember when we did Hess's law on delta H, whatever you did to the reaction, you did to delta H. Same with delta G. Not with E. Whatever you do the reaction, you do not do anything with E. When we're talking about E cell, these numbers are unchangeable. You cannot alter these numbers. You will not multiply these numbers by anything, nothing. They stay as they are, never multiply them, never adjust them, never divide them. They are only added in oxidation plus reduction. Okay, so now I think the easiest way to talk about this is an example. So let's look at one. So what I've done here, so what we're going to do is we're going to calculate the E cell. So we're going to say, like, will this reaction occur? And if it does occur, what's the potential? Now, here's our reaction. It's all nice and beautifully balanced for you, right? All pretty balanced. So what I did was I went to the table and I found these reactions. So I looked for the aluminum going to the aluminum 3+. So I just want to go to the table to show you where I got this. So aluminum to aluminum 3+, there it is. So I went into the table and I just copied and I cut. So usually what I would do if we were in class, I would pass this table out to you and then you would like look at it yourself, but obviously we can't really do that right now. So I just copied and pasted what I got out of there. Okay, the next one was this, the NO3- to NO2. So I went to the table. NO3-, and I want you to notice something for a second. Look at this one. This one has an NO3- in it. There's another one here. It's easier to look at. I don't think that's the same one, but there's multiples, and there's multiple oxygens and multiple waters too. So we're going to talk about that one in a second. But anyway, this is the one we used for this one, easy peasy. And again, you're just looking for the elements that match, right? And then there's our two waters. Then here's our aluminum. I'm going to put boxes around it so you can see it. And our aluminum 3+. So we just go to the table and we figure out which one we have. The next thing we do is not just give you the answer. The next thing we do is we look at, again, written as reduction potential, written as reduction potential. When one is oxidized, the other one must be reduced. So if we look here, aluminum is going to aluminum 3+. So this is going from aluminum to aluminum 3+. That's backwards, right? That's, sorry, my plus didn't come through. Plus 3 electrons. So as a reduction, it's negative 1.66, but this was oxidized. So it's positive 1.66, right? Because you see how it's the opposite. So we flipped. Go ahead.
So when it's oxidized, the electrons need to be with the products, right? And if it's reduced, it needs to be with the reactants?
Yes.
Oh, okay.
Yeah, because remember, lose electrons oxidized. So this is on the exiting side. So it's losing them. And if it's reduced, gain electrons reduced. If it's gain, it's going to be on the entering side. Yes, but great question. So this one, if this one was oxidized, again, because we looked at the way it was written, it was Al to Al3 plus. That means that our other one must be reduced. So, oops, let's just do it to check. Yeah, NO3 minus is in the reactants, 4H plus is in the reactants, NO is in the products. This is the way it's written. So our reduction is NO3 minus plus 4H plus, oh, I wish I would have written this so it was more together. It's okay. Plus 3 electron goes to NO plus 2H both. And then this will stay the same. And I like to put my pluses and my minuses to make very certain to myself what's happening. And so I'm just going to move this over here a little bit. Negative 1.66. So when we add this reaction, our electrons cross out and we end up with aluminum plus NO3 plus 4 hydrogens goes to aluminum 3 plus NO. I'm not putting the states in because you can see the stage plus water. And then we add this here. Oops, that got a little big. We add this also. So when we do that, we get, I don't know where the plus went, plus 1.66, remember, because we flipped it, plus 166 plus 0.96. So our potential is 2.62, right? Yeah, 2.62. That sort of looks like a 6. So this reaction will occur, right? And it will occur in the direction that is written because it's a positive electrode, and we're going to talk about that more. Okay, questions on this? No question is too small for this. Okay, so I'm going to summarize what I did. I looked at the reaction they gave us, and then I went and found the reactions on the table. Then I found out if the reactions were going in the way that were written or backwards. Aluminum was going backwards. So therefore, I flipped my sign to positive, and then I add them up. When I add the reaction, it better look like this in the end, right? Now, when you get good at this, you'll literally do it in 20 seconds. But right now, we take a little bit more time. Here it is. I knew I had a meter and just saw that. Right? And so again, I flipped my 1.66 because it was the opposite that was written. This stayed the same, and then I just add them together, and I get 2.62 volts. And again, I like to put these positives on here and be very, very cognizant of the plus and minuses, because that's kind of the whole part of this, and it's really easy to make a mistake on those or not be able to see them. Okay, so let's try another one. All right, actually, I'm going to give you a minute. I want you to try this one, and we're going to go over it in just a minute. Just give me 30 seconds for some of you are going to be able to see it right away, and then just type your answer in the chat. And those of you who don't see it right away, we are just starting this. It's okay. I'll go through it in just a minute. Okay, let's go through this one. So we look here and we see IO3 minus is in the reactants. Okay, IO3 minus. I'm not just going to do IO3 minus. Let's just check here. And then 3 I2s. Oh, yeah, there's our I2s. And again, what's going on with this? And then, oh, we got an I minus here. So it looks like we've got multiple things going on. All right. So when we do this one here, we need to kind of see what's going on with this one. So we got IO3 minus, so let's just write what we have. So it looks like we have obviously these two reactions, right? So we have these two reactions. So we've got IO3 minus plus 6 H pluses plus 5 electrons goes to 1/2 I2 plus 3 waters. What a weird one, right? And that is plus 1.2. Our next one is I2. Plus 2 electrons goes to 2 I minuses. And this one is plus 0.54. Okay, so now, right, we either add them or we subtract them, right? Or we have negatives of both, right? One of them has to go forward, one of them has to go backwards. The question is which one's going forward and which one goes backwards. And so you can see here, you're looking kind of for like a difference in here. So this 6H plus is similar to that 6H plus, right? This IO3 minus. And then the 5 electrons, right? It's not quite working out with the electrons, but obviously we're going to have to multiply by the electrons to make this work. Okay. This one's obviously going in the forward direction, right? Because the IO3 is here, the 6H plus is, it matches enough. It's going in the forward direction. It's just staying plus 0.2, right? Let's look at this one. If that one's going in the forward, this one has to go in the backwards. It has to go backwards. So this must be 2 I's goes to I2 plus 2 electrons. If one's going forward, the other one must go backwards. So this is negative 0.54. So your answer is just going to be 1.2 minus 0.54, which equals 0.66 volts. If one's going forward, so let's say you're like, how did I know it was going backwards? Well, what I did know was one of them was going forward. This one was going forward. They are paired together. One goes forward, one goes backwards. One's oxidized, one's reduced, right? This one here has the electrons on the entering side, right? So it is reduced. So this one has to have electrons on the exiting side. It's oxidized. Gain, electrons reduced, lose, electrons oxidized. One's oxidized, one's reduced. Has to be a pair like that. And then again, if you look at it, our electrons don't match, right? So we're gonna have to multiply our electrons through, but we don't really need to because you don't ever change these. And they didn't ask us anything about that, but you never change. These numbers never change. So you can do whatever if you have to multiply, this one by 5/2 and the other one by 2/5, or multiply this one by 2 and that one by 5 to get to 10, it doesn't matter because you're not changing these numbers. You can if you want to do all that work, but you don't have to do all that work. Once you know this one's going forwards, this one has to go backwards. And so you just flip the sign and you get 0.66 volts. Okay, so now I'm going to summarize everything we just did, and then we're going to keep doing it again. Okay, to summarize how we use this table and what it does. So what we've been looking at spontaneous reactions, reactions that are positive. So if you have a strong tendency for the oxidizing agent to be reduced and the reducing agent to be oxidized, what does this mean? If you're higher on the table or more positive, then it's a stronger tendency to be reduced, more likely to proceed in the forward direction. Because remember, the more positive it is, the lower the potential energy. Positive, right, attracts the electron. The electrons come towards it. If we're lower on the table, more likely to be oxidized, more likely to proceed in the reverse direction. And remember, the more negative it is, the higher the potential energy. The negative charge is going to repel the electrons, right? The more negative it is, the electrons want to leave it, lose electrons, oxidation, right? So the more negative it is, lose electrons, oxidation. The more positive it is, the more likely it is to gain electrons, reduced. This is a very big, important slide. It kind of summarizes everything we just did. So now, how do we predict which way the reactions will go? So let's say you have a cell, and the cell that we've been looking at has this in it. And we have two reduction potentials. How do we know who's going to be oxidized and who's going to reduce? So how to make it spontaneous or non-spontaneous. So if you look at this, if we look, see this one is a negative and this one's a positive. And so let's just look at this for a second. The more positive it is, the more likely it is to be reduced. So the more positive it is, the more likely it is to be reduced. This is more positive. This is reduced. So this one is more likely to be reduced. The more negative it is, the more likely it is to be oxidized. This is a reduction potential, so we have to flip it. Flip it, and then we flip this also. But we don't have to worry about these right now because here's our spontaneous reaction where zinc is going to go from zinc 0 to zinc 2+ because we flipped it, where zinc is oxidized and copper is reduced. This would be non-spontaneous. And remember from our exam we just took, if it's spontaneous in one direction, it's non-spontaneous in the other. So I'm going to give you a really quick, fast way to be able to tell what happens with a reaction. A spontaneous reaction will take place when a reaction is paired with an oxidation reaction lower on the table. And I'm going to show you what this means. So if paired the other way, a reverse reaction occurs. So basically, here's my statement. How do I say this? I actually think I wrote it in my PowerPoint. So any half reduction is spontaneous when it's paired with the reverse of a reaction below it. What does this mean? So here's a table. So if any reaction is spontaneous, if the reaction on the top is written in the forward direction and the reaction below it is flipped, it's spontaneous, right? So any reaction occurs when the one higher on the table goes in the forward direction and the one below it is flipped, meaning oxidized. It will be a spontaneous reaction. Okay, so let's try this one. Predict if the following reaction is spontaneous, meaning will it happen under standard conditions. Okay, so remember, higher on the table, more likely to be reduced, more likely to go in the forward direction. So let's see here. We've got iron. Okay, iron, backwards, right? So it's backwards. Plus 4.5. And then Mg2+, forward, negative 2.37, it stays. Now remember what I just said. Any reaction is spontaneous if the reaction on the top is written in the forward direction and the reaction on the bottom is written in the reverse. We do not have this case here, right? We have this one reversed and this one in the forward direction. That's going to be non-spontaneous, right? So here's those two reactions. Again, I just separated them out. And so again, using the rules we just talked about, because the magnesium is below our iron, it'll be non-spontaneous. So in order for it to be spontaneous, the reaction higher on the table has to be written in the direction, the reaction has to be written in the direction of the table. The one below it has to be flipped, meaning oxidized. So now, if it's non-spontaneous in one direction, So this is not spontaneous, meaning the other way is spontaneous. So if we had Mg solid plus Fe2 plus goes to Fe solid, AQ plus Mg2 plus, this would be a spontaneous reaction. So I'm going to prove that in 2 ways now. Okay, so here are the reduction potentials again, right? And so if we look at this, our Mg is now in our product, so it's flipped. So this is now a positive. Our iron is now written in the direction, so this stays negative 0.5. So when I add these potentials, oops, I'm trying to make this so you can see the difference between my positive. When I add these potentials, I'm going to get a positive number, right? And again, positive number means it is going to be spontaneous. So 2.37 minus 0.45, 1.92. 1.92 positive. Now, let's say, and I won't make you do it on the quiz today, but let's say I asked you to draw this, right? So if I asked you to draw this cell potential, the question is, how would we draw this cell potential? So we're going to do that right now, except for my computer is popping up crazy things everywhere. Okay, so how would we draw this cell potential? That's what we're going to do right now. So how do we draw a cell potential? One beaker, the other beaker. I'm going to make them a little closer together so my salt bridge isn't so big, right? You have to have an electrode in one, and you need to have an electrode in the other. In this case, magnesium is oxidized, right? How do we know magnesium is oxidized? Again, it goes from Mg to Mg2 plus. We look here, this is the reduction reaction because we write them all as reductions. We have flipped it. So it's going to be flipped. Now it is an oxidation reaction. Oxidation because it lost electrons, lose electrons, oxidation. So that means that this is our magnesium. And this is our solution. We have magnesium 2 plus in here. Our reduction is our iron, is our solid, Fe2 plus here, right? We need some kind of a salt bridge. That's my salt bridge. I can't draw. And now our salt bridge, we have to decide which one's going which way or the other way, which we'll talk about in a second. Then we have to connect them by a wire, right? And again, this is our oxidation, lose electrons, oxidation. This is our reduction. Oops. Gain electrons, reduction. And I want to remind you of this. Leo, the red cat, goes grr. My pen. Meaning reduction happens at the cathode. So if you're like, I don't know which one it is, the one that got reduced, this is our cathode. Meaning the other one is our anode. It only has one end. Okay. Now, the other thing we need to do is decide which way are the electrons going. Now again, remember, the electrons will go from, they lose it from the anode, gain it at the cathode. Oxidation loses electrons, reductions gain. electrons. So the electrons are going to go this way. Other way to think about it, this, if you're oxidation, you have a higher potential energy. Reduction, lower potential energy. Always goes from high energy to low energy. It's like a waterfall, only goes one way, right? If we look at this, our magnesium is a plus 2.37 volts, and our iron is a negative 0.45 volts. Okay. Actually, I'm not going to do that right now. I want to do the cell potential before we do this more. I mean the cell notation. Let's look at the cell notation. So remember, in our cell notation, we always have our solid. So it's always oxidation on one side, reduction on the other. Oxidation is always written on the left. So if we look at this, we have magnesium as our solid, our phase change, MgAq, 2 plus, salt bridge, Fe, 2 plus, AQ, different number of phase, aqueous versus solid, Fe, solid. So this means this, right? So they literally mean the same thing, right? It's like this big picture is the exact same thing as that cell notation right there, right? So if I give you cell notation, which I will not do that this quiz, not this week. You will not have to do this week. Next week, yes, you will. But if I give you a cell notation, you should be able to take that cell notation and put it into a picture. Now, oh, what about our salt bridge? I don't know, let's use NaCl. Na is not usually a good one to use, but whatever. We're going to use NaCl. So that means we've got Na pluses and Cl minuses, right? So if our electrons are continually going this way, this is eventually going to become negative. So our Nas are going to balance it out. So they're going to go that way. If the electrons are continually leaving this solution here, that means our chloride ions need to go this way to try and balance it out. I think that's everything that we have here. We can add so much more to it, but I think this is good. All right, any questions on this? This might hurt your brain, but it's so much fun once you get it. Okay, so I have it prettier. I don't have all the detail I have in this picture, but I do have it nicer over here. So here's kind of the same thing. It's nicer, but I don't have all the details again. So I just put salt bridge. So in this case, we had Na. It's going that way. Cl minus is going this way. When we did our cell notation, Mg, solid, Mg, well, you already saw the cell notation. I don't need to draw it again. Okay. All right. This one's for you. Now, I want you to think about this one. Try this one. So I want to know if it's spontaneous as written or spontaneous in reverse, right? If spontaneous the way it is written or spontaneous in reverse, right? So try this one and then we're going to go over together and I'll give you like 2 minutes to do this one and we'll go over it. Okay, so what we're looking at here is we're looking for, I knew I had this written somewhere here. I wrote this for you. So any reduction half reaction listed as spontaneous when paired with the reverse below it, which means top reaction goes forward, bottom reaction goes backwards. It's spontaneous. It will proceed in the direction written, right? So we just looked. Okay, F2, that's going forward. So we're just looking for I2. Looks like it's this one. Is it going backwards? Yep, it's reversed. This one is spontaneous in the way it's written. Yep. Next one. Oops, that was supposed to be an erasing. MG. MG. That's backwards. Okay. AG. I like to look at you can either look at the ions, whichever one you want to. So this is written forwards, right? The AG is written forwards. This is written backwards. Spontaneous. Next one. CU and I. You have to be careful with I's because there's a couple different I's. Let's try. Yeah, because this one has a 2I, so it's definitely this one. I2 and 2I. Okay. Whoop. Okay. This one's written forwards. CU. CU is also written forward. Nope. Non-spontaneous. It's spontaneous going backwards. Backwards spontaneous. All right, let's look at this one. CU and CR. So CR3 plus. So this is flipped. CU is written. So this is going forward and this is flipped. This will be spontaneous. So you see how there's like the long way you can think about it in like great detail, or you can just remember this little piece right here, which just is the way when I just do it really quickly, I just remember this. It doesn't use a lot of the theory, but it's applying and it's just like a shortcut when you have a small question. All right, let's look at another one. Which of the following materials can be used to oxidize copper without oxidizing silver? Okay, so oxidizing, meaning it wants to lose electrons. So we want this to go in the backwards direction. But we want this, so we want to oxidize, we want to flip this one, but we do not want to flip this one. Right, so we want this one to stay that way. Okay, so we want to flip it because remember we want to oxidize copper, lose electrons, oxidize. We want it to flip. So we look here. That's not really even an option because it should say F2. Mi minus. Again, it's not really an option because it's a product, right? We're looking at what if it's got to be in the reactant has to do this. Oh, this one could, right? Because if this one goes in the forward direction, then this one could go in the backward direction. So that could work. Let's do chromium. Nope, it's below it, right? If it's below it, this would end up being oxidized. So our only choice is I2. This is our only choice. So again, sometimes it's a little bit of a trial and error when you're doing these, and it takes a little bit to get used to. So if you're seeing this and you're like, what? I don't know what she's talking about. You need to read your book, right? And then come back to this again and watch the part where I went through the cell notation again. So last problem we're gonna try. This is what a question would look like, not on your quiz this week, but definitely on your exam for sure, and maybe on your quiz your quiz next week. Again, this week's quiz is just like, what's the oxidation state? Who's oxidized? Who's reduced? How do you balance oxidation reduction reactions? Things of that sort, right? It's this stuff right here. We're not ready to do a quiz on this yet. Your quiz is only on your Chem 101 Electrochem Part 1. Okay, so I'm going to give you a minute. Try this question, and then we're going to go over it together. And by the way, next week you will be doing questions like this on your quiz and for a lecture quiz also. So try this now, see how far you can get, and then we'll go over it. Okay, so we're gonna walk through this very slowly. So we've got silver in silver nitrate. So again, nitrate, but doesn't matter, Ag plus. So it must be this reaction we're talking about. Okay, the other one has a platinum electrode. Okay, interesting. And it has Cr, again, this nitrate, this is 2 plus, and chromium 3 plus. There it is right there. So these are the two reactions we've got. Does everyone see how I got that part, right? I just went and looked for the table. Okay, so now we have to decide which way it's going to go. So remember, the higher up here, the more likely it is to be reduced. The lower it is, the more likely it is to be oxidized. Reduce means gain electrons. Reduce means written in the direction that it's already done, right? So gaining electrons, right? So that means that this one will be reduced. I'm going to use GR, gain electrons reduced. So this one right here, this one's going to be reduced. And that means that this one's going to be oxidized. All right, any questions on how I figured that part out? So remember, to be spontaneous, a reaction that's higher on the table needs to be paired with a reaction that's flipped below it, right? The overall reduction potential needs to be positive. And if one gains electrons, the other one has to lose electrons. So that means that this reaction is going to be flipped. So it's actually going to be Cr2 plus goes to Cr3 plus 1 electron. And this is going to be plus 5. Right? Okay. Now, if we're going to draw the potential, one beaker, another beaker, gotta have an electrode, gotta have an electrode. Ooh, that's the skinniest electrode ever. I'm never going to be able to write on that one. So again, if you're like, I don't know how to do this, you can draw a beaker and an electrode. And I don't know, let's put some solution in here. And we know that there's got to be a salt bridge, right? And a wire that connects them. So everything looks like that. Every time you draw it, this is the first thing you do. We haven't put anything in there, but this is what the basis of a voltaic cell looks like, okay? Now, we got to decide. So let's put our oxidation, because when we write our cell notation, the oxidation has to go on the left. So let's just put our oxidation here. And again, it doesn't always have to be written this way, but we're going to do that now. I could have flipped it. Just remember, when you write your cell notation, it has to go on the left. So that means our oxidation reduction is our Cr2 plus Cr3 plus 1 electron. I know this is kind of small. Okay. All right. So our anode is platinum, right? Because it said it was a platinum electrode. And in here is Cr2 plus and Cr3 plus. Both of them are in there, okay? Our reduction reaction is Ag plus 1 electron goes to Ag solid. So our electrode is Ag. The ion is Ag plus. Now remember, Leo, the red cat goes grr. Reduction at the cathode, right? So this is our cathode. This is our anode. Which way are the direct electrons going to go? This one is gaining electrons. They're on the entering side. They're entering the equation. This one is losing the electrons. So the electrons will always go towards the cathode. Always go towards the cathode, right? Because the cathode is attracting them. So if we look at this potential right here is 0.8. This potential here is 0.5, right? And so this one is more positive. This is more positive, so the electrons are going to be attracted to it, right? That's why, see how neither of these are negative, but this one is more positive. So the electrons are going to be attracted to it, right? And so the electrons are attracted to the more positive electrode because negative is attracted to positive, and this is a less positive. So when we do this, when we add this, our E cell is just going to be 0.8 volts plus 0.5 volts, or 1.3 volts. And my sig figs aren't right, but let me just fix my sig figs. It's 1.30 volts, because when you're adding, you look past your decimal place. This is 2 places, this is 2 places, so this has to be 2 places, right? Remember that from Chem 209. Okay, now, salt bridge. I don't have enough room to write this. But the positive one is going to go here, so I'm just going to do NaCl again. So the positive Na plus will go towards the electrons. The Cl minus will go away from the electrons, right? Because it wants to even it out. If we were going to do our cell notation, I'm trying to figure out where I can do this. I can do it right here. So if we're going to do our cell notation, you know what, I'm going to erase this because I want you to see it under here, but that's fine. You don't need this. So if I said, what's the cell notation, which summarizes this entire picture up, you have your platinum electrode, and then remember that's a solid, and then you have Cr2 plus aqueous, comma, Cr3 plus aqueous. It doesn't matter which one you put first because they're both aqueous. Salt bridge, Ag plus aqueous. Phase barrier, Ag solid. So those two kind of go together with each other. Okay. Any questions on this? I'm sure I have this meter. I wouldn't have just left this blank. Oh yeah, oh, so much prettier. Except for these are supposed to be E cells, not E boxes. Okay. Questions on any of this? Brain's probably hurt right now. It's like one of my favorite lectures because it makes you think so hard. If you're confused on this, make sure you go into your book. You have to read your book on this part of electrochem because you really need to understand positive potentials and the negative potentials, reduction, oxidation, right? Chem 101 really helps walk you through it. Again, your Chem 101 won't be on this advanced stuff. It's going to be on more of the basic stuff this week. I think we're going to end there today. Also, if you are having trouble, come back to the video and write this stuff down that I have on these slides right here. I think this really helps kind of keep it in your brain, right? Or it makes it stay in, because it doesn't stay in your brain right for a while. It takes a little bit. This helps solidify it in your brain. So come back to these or write it down in your book or on a piece of paper to help you remember it. That kind of like helps keep it in your brain correctly. Okay, so let me just go back to our picture where we ended. And there we are. Okay, so any questions before we finish today?